Up next is an overview of a performance-based design and implementation of an SHM system on a complex/signature bridge for a DOT. Nathaniel Dubbs, went with Nathaniel, Associate Vice President of Testing and Monitoring with Bridge Diagnostics.
Thank you. Good morning, everyone. And yeah, Nathan Nathaniel's fine. I'm just not Nat. I'm not a bug. So that's the only thing I ask. So yeah, good morning again. Thank you for having me. The points I wanted to go through in the presentation today, just an overview of SHM very briefly for those that may not be familiar, discuss a little bit on the potential for integrating within asset management, and just a little bit more of a reviewed case study on a signature bridge, and just walk through, and like the title of the slide or the presentation suggests, really looking at deploying instrumentation with a performance-based design approach. So what specifically are we looking to learn from the instrumentation, taking the decision-making into mind when we're putting the sensor and instrumentation layout and design in place, so that we're thinking through how we're going to use the data before we actually even put a single sensor on the bridge. So that's really the case study that I want to go through this morning. And then go through just a few other brief case studies of signature bridges that we've done throughout the country. And then finally, as time allows, I'm also the co-PI for a project with Federal Highway Administration on putting together best use practices for structural health monitoring, and actually expanding a tool that Federal Highway has through their info technology program to include structural monitoring technologies. And I should note too, Federal Highway is taking the initiative to drop the health from structural health monitoring and just embrace structural monitoring to kind of avoid some of the connotations with the health diagnostics imaging. Bridge Diagnostics, we've gotten more than our fair share of people looking for COVID testing over the last few years. So I think we even have it right on our website, the contact us page, is we are not a medical diagnostics company. We are a structural engineering consulting firm that does instrumentation and non-destructive testing. Okay, so what is structural health monitoring? There's many definitions. I think there's even a Wikipedia page for it. I like to define it as the practice of identifying and tracking performance metrics through measured data and some type of analytical models. That could be a back-of-the-envelope understanding of structural mechanics. It could be a finite element analysis. Generally speaking, we're taking measured responses that generally we're not interested in. A single strain measurement or a measurement of displacement, typically I don't care and I don't know what it means. What I'm interested in are these other performance states. So what is the condition of the bridge capacity? Is there damage? What's the remaining service life? These are the things I'm trying to get that I cannot directly measure. So the challenge is, how do we translate the things that we can measure but we're not directly interested in into the things that we're trying to achieve but we can't directly measure? So that's a little bit about the case study that we'll walk through. So why and how do we do structural monitoring? Typically, they fall into one of three categories there. We're trying to get a better understanding of structural performance, and it could be for a variety of the reasons that you see under that bullet. Inspection support certainly is a large one. We work a lot with consultants doing inspections that happen to find things out in the field, and they just need to know in better context, more than that point in time, what's happening. Is this crack moving? Is the structure moving? We found it in this certain condition or certain state, but how is it performing over time? And that's typically where we come in and support. And then finally, from an operations and maintenance perspective, especially with movable bridges, complex signature structures, this is where integrating in an O&M plan, asset management plan, really makes sense for long-term permanent instrumentation, maybe not necessarily for your run-of-the-mill bridge inventory. But generally speaking, we have that need to keep a remote eye on potential problems. And again, this is where, integrating with RWIS, roadway weather information systems, way-in-motion systems, bridge way-in-motion, you can see the potential for integrating a lot of the existing ITS type information that's being collected into a more holistic asset management system. And then kind of the process you see there on the right is a design process that I like to try to embrace and encourage. So this helps avoid the exercise of throwing out a whole bunch of sensors and then trying to figure out what to do with it afterwards. I went to grad school. I had the pleasure of going through and putting out a whole bunch of instrumentation and seeing what we could learn from it and writing papers, writing a thesis, giving all kinds of presentations. But at the end of the day, when we're talking about applying this in practice, we need to approach this with a more intelligent and thoughtful consideration up front. Deploying technology where it's truly needed. And again, as the previous speaker said, this isn't applicable for every single structure. So working with consultants and owners up front and identifying where we could actually get value and return on investment of this up front. And this workflow kind of helps walk through that. So I'll use this to guide some of the next few slides. So after, typically, and I'll just back up a second, the first 2 points there are typically have already been done by the time we usually see a phone call. So a lot of times the problem's already been identified and people are saying, is this an appropriate application for deploying technology? And that's where we'll work together with the structural engineers and owners to say, okay, yes, this is something we could measure. This is potentially able to be converted into a performance metric that we could help you inform. Now let's move forward through the process. So fundamentally, we need to ask, okay, what are the inputs of interest, and then what are the outputs? So if I'm just interested in overloads crossing this bridge, I need to understand, okay, sure, I can measure strain, using that to estimate what loads are going across. But what other contextual forces is that structure being subject to that could also produce measurable strain, temperature changes, settlement, so on and so forth? I need to capture all those things too, so that I can give you a more accurate understanding of what those loads are going across. So just walking through that process, that helps inform the instrumentation design, and then from there, going out into the field, doing the actual instrumentation and putting some performance criteria against this. And then one point here that's important to make, a lot of times we can, the measurements are able to be directly informed. If I'm interested in the underclearance of a bridge, that's a single measurement, bridge to water, measuring that air gap, I understand it intuitively. It doesn't need any fancy processing or interpretation. It's directly interpretable. But if I'm looking at like displacement versus temperature, a lot of times, for an expansion bearing, that might not be as straightforward as you would expect. It could be a somewhat complex response. So the little graphic you see on the lower right, maybe that's a year's worth of data. And anything within those 2 lines I'm happy with, but it's that green point that I want to know if I'm starting to get measurements over there. So that's where it just takes a little bit of an advanced step ahead, some kind of statistical analysis to look at when we should be getting an alert from the system to know that, hey, we need to go out, deploy an inspection crew, and look at our expansion system. And finally, from an asset management perspective, what are some of the issues where I think monitoring really could help? Certainly if there's unknown conditions regarding the structures, no as-built, foundations, unknown material properties, those are always structures that are good candidates for load testing, instrumentation, non-destructive testing. Changes in regulations, same thing. Obviously, if we have different rating requirements, again, those are good case studies for deploying technology like this. And then certainly with monitoring, looking at efficacy or life cycle costs of innovative or new rehabs, designs, construction staging. We do a lot of work with erection engineers if they're deploying new or somewhat complex or risky construction erection techniques. Having that situational awareness certainly just helps put everyone at ease. Okay, so I'm going to walk through a little bit of a case study here for a signature bridge. The owner did ask to keep their name and the name of the bridge out of the presentation, and they said it would allow me to talk a little bit more freely about some of the conditions of the structure. So you will see pictures of a few different bridges. Those are just illustrative examples and not necessarily the structure at hand. But a little bit about the structure. It is a cable-stayed bridge, post-tension segmental concrete construction, and there's a host of issues on the structural performance related to the post-tensioning system. There's transverse cracking in the segments, joint openings in the segments, web shear cracks, and generally speaking, an uncertainty around the state of the post-tensioning system. So this was really a driver of a lot of the global monitoring system that was designed and put in place. So BDI actually worked together with, starting with a document that WSP had put together. They were the engineer of record for the rating of the structure, and they put together a host of suggestions and recommendations for monitoring. So we started with that. It was a great reference point because they already established these are the criteria that we're concerned about where we think monitoring could help. So working together as a team between the three parties, we identified these 5 performance states that we were going to design the monitoring system around. So looking at transverse crossover tendon performance, that was one that was highlighted of interest. The joints of the box girders themselves, looking at the precast segmental post-tension column performance, the pylon, and then finally the stay cables themselves. I think there was a presentation yesterday talking about using vibration and acceleration measurements on stay cables to infer the in situ force, so that was one thing that they were interested in. So here's a schematic. It's a delta frame type construction for the suspended spans, and you can see one of the crossover tendons there that the owner was just concerned about. And again, I think there might have been grouting, QC issues, things like that during construction. So just the ultimate concern here was, what if we lose a tendon? How can we know and deploy a crew out to verify with inspection and then put in some kind of rehab or assessment of the structure? And so the approach that we put together with WSP here was, you can see a line of strain gauges there on the right-hand side. Obviously, this was mid-installation. All the sensor coils are still there. The cable coils are still there. But essentially what we're doing is, and let me see if I can get that laser pointer up too. Within the median section here is where these line of strain gauges are. And what we're doing is assuming that if we would lose the post-tension force in that strand, the force obviously has to go somewhere. It's going to go into that concrete deck. So putting that line of strain gauges in this section here allows us to capture that force transfer if it were to occur from the post-tension system into the concrete. Okay, so that was one. One of the, again, the second concerns was just the performance of the post-tension box girder system itself, or the segmental construction itself. So there was 2 approaches here. One, you can see a typical tendon layout with all the different segments in place. So using pretty straightforward instrumentation, crack meters, displacement sensors across those segments, and additionally capturing a good representation of temperature. So again, we want to get as much contextual measurements as we can to understand, is it temperature related, live load related, or some other phenomenon that we haven't yet learned. Secondarily, we also wanted to capture the global movement of the superstructure itself. So how the expansion bearing's performing. Here you can see a displacement sensor, again, kind of mid-installation, capturing segment to segment measurement at a expansion bearing. So looking at how the units are performing and expanding and contracting as temperature changes, and any existing kind of flaws that were identified through inspection, how those are changing over time. With respect to the columns, there's a few approaches here. So one, you can see a fairly precision crack meter on the left-hand side being installed out of a snooper. In the middle is a tilt meter. So naturally, this allows us to track the position of the piers over time. The piers were instrumented at 3 locations, one near the bottom, one in the middle, and then one towards the top. That just allows us to understand, is the pier moving in a flexural shape or a rigid body shape? Obviously, that informs a lot about the condition of the foundation and whether there's any loss of rigidity towards the foundation of the structure. So that was certainly something of interest for the owner. And then finally, there's 2 different ropes access pictures here, one on the outside, one on the inside. 2 different pylons, obviously they're different shapes. Looking at the pylon performance itself, and this just goes to show some of the challenges that we face on the instrumentation. Obviously, we got to get into some pretty challenging places, so using ropes access is a great tool. On both of these applications, on the left, we're actually instrumenting that tower with tilt meters, again, at multiple positions along the height of the column, so we can infer what kind of shape it's moving at as the temperatures change. And on the right-hand side, that was a structure that similarly had exhibited some cracking on the outside of the pylon. So that engineer is putting some crack meters in place. Actually, I think he was doing some maintenance. It was a little bit formidable situation there with all the red lights. I think it was in October around Halloween time, so it was like a little eerie when we were out there. Of course, right, that was the only time we could get out and do some sensor maintenance, when he was getting blasted in the face with bright red lights. Finally, I mentioned stay cable performance. I won't belabor the point. I think the speaker yesterday did a good job of explaining typically how this is done. In that case, they were doing a short-term measurement of acceleration to infer the stay cable forces. This can also be done permanently. This owner had deployed, I think, this type of testing every few inspection cycles, so it was pretty clear to them to say, okay, we could just make the upfront investment now, let's just permanently instrument it. We get this measurement continuously over time, and that saves us that recurring cost of having someone go out to deploy all this testing. Because as you can see, it typically requires a lot of man lifts, lane closures, things like that. There's a lot of support required just to get out in the field, take these measurements. So probably within a few inspection cycles, they've got an ROI on that. And if you're curious on doing this yourself, you can see the equation there on the lower right-hand side. You get your frequency. I will say this, the two biggest uncertainties that you have to consider when deploying this method is you've got to know the length of the cable. Fair enough, we should be able to measure that. But the bigger challenge, especially with older structures, is you need to know the unit mass per length of the cable. Like I said, newer structures is probably part of the design specs. That's fairly easy to get. But with the older structures, that can be significantly challenging. And it's this term right here. So any uncertainty in that number directly carries over into your computation of the tension force in the cable. So a lot of times we'll say, this is plus or minus 10%, and that may or may not be good enough, at which point we say, well, we need a sample of the cable to get that unit weight nailed down with 100% certainty. So just something to keep in mind. So those are all the measurements, and then kind of tying it all together to make it happen. What is required from an owner's perspective of really deploying a system like this? Well, it requires a bit of hardware, especially for an application like this. It was a permanent installation. So you're talking about ruggedized, hardened cabinets to house all your data acquisition. It needs power. It needs communications. The system itself needs maintenance. It's not unlike any other computer or technology system that's being deployed. It needs to be checked and maintained just like any other piece of infrastructure on your assets. So again, putting cables into conduit, you can see an example of that over here, and everything into ruggedized and hardened cabinets. Next steps, the system's been up and running for this specific structure since, I think technically October. We officially started the clock on the website and everything in January. So we're gonna be doing 6 months of monitoring for baseline period, just understanding from the coldest cold to the warmest warm that the bridge typically sees, what is a normal day in the life of this structure. And from there, we're gonna be working together with WSP to put together alerting thresholds and requirements. So at what point is the owner notified? At what point are we notified, WSP, so on and so forth. So now it's more automated. We don't need to go in there and manually intervene with the system all the time. So again, we'll be, for those few objectives there, really the practice that we're in now is establishing what does normal behavior look like. All right. A few other examples. This is one in Arizona for more signature complex structures. This bridge had a lot of issues with fatigue cracking, and this was a fairly comprehensive integrated system, traditional structural monitoring, strain-based measurements. You could see a rosette down there in the lower left. Weigh in motion, acoustic emission monitoring. This was really a comprehensive approach towards getting more accurate information as to what's happening out there in the field. This was in a very remote location in the upper northwest corner of Arizona, but on a very critical corridor for the state. But you can see it required, I won't say a small solar farm, but a pretty robust solar design of panels and batteries to support the system, because obviously there was no power out in this location. And this, again, with that kind of a complex, comprehensive system, I think there was even cameras out there too that were triggered off of the strain measurement. So if there was an overload, you could get a video of that vehicle crossing. And more often than not, what we saw was multiple vehicles, right? But that's still good to understand and have that context. Okay, thanks. All right, this is Sunshine Skyway. We've been monitoring this one again for stay cable performance. Talked about that quite a bit. Henry Hudson Bridge, actually this was a project that just wrapped up. There was pretty significant rehab on the skewbacks of the arch. And so naturally, owner was concerned about state of the structure itself, but also the repairs of the skewbacks. It was basically a redundant load path that was put in place in the foundations, and they're monitoring to see if that redundant path ever engages. So kind of a dual monitoring approach there. All right, I'm gonna skip ahead. I wanna talk about this a little bit and then I'll wrap up. I have like a minute? Okay. I mentioned that we're working on a project for Federal Highway related to a structural monitoring web manual. And so like I said, Federal Highway has this. If you just Google Federal Highway Info Technology, you'll probably get to this landing page. And then currently, if you click on Bridge, you'll get something like this. And you can click on the left-hand side, go through and navigate to, if you've got a specific concern that you have, you can go through and click, and it'll recommend, in its current form, non-destructive evaluation or testing techniques relevant to your application. Steel, girder, cracking, probably do ultrasonic testing, things like that, right? So what we're working on is providing the complementary structural monitoring technologies as well. And we're hoping that this will really help provide owners and consultants a really strong toolbox to understand, hey, I have this guy from BDI coming in my office saying that monitoring is the best thing in the world. But what are the pros and cons and limitations of this? Is strain monitoring really appropriate for fatigue applications? So it's a Federal Highway sponsored initiative to putting more education out there for the use of monitoring. And it's a charge that we're leading. And no, they're not going to let us say use BDI for all that monitoring. So these are some of the things that'll be included. What are the typical targets, physical principles, what's required from data acquisition processing, how do you interpret it, disseminate it, pros, cons, and then references. We did a very comprehensive lit review for case studies and things like that, so you can actually go out and actually speak to folks that use that technology. So I don't want to run too long, but thank you for your time. Any questions?
The preceding was produced by the National Center for Pavement Preservation. More information can be found on the web at pavementpreservation.org. Additional support provided by Michigan State University.